This call is now being recorded.
Good evening, everyone. Today is class 3 of Aksharamaala course. I'll be teaching physics again, and we shall continue where we left in the last class, which was Rutherford's model of an atom, the drawbacks for it. Let us quickly see what were the drawbacks of Rutherford model. So it will be easier to connect drawbacks of Rutherford model of the atom. So there was only one big drawback of this model of the atom. Let me check if the audio is coming. So yes, it's so according to Rutherford's model of an atom, there is a nucleus at the center of the atom, which contains all the positive charge of the atom and nearly the entire mass of the atom. And electron will orbit around it and in circular orbits. Okay, electron is bound to orbit around the nucleus in circular orbits. But it did not mention about the orbits much. It only mentioned that it will be circular. But according to electromagnetic theory, orbit when the electron that is a charged particle when accelerating will produce EM radiations. That is, it will radiate away its energy. So when electron is moving in a circular orbit, its velocity's direction changes. That is, it is accelerating charged particle, which tells us that the electron is gonna radiate EM waves and it will keep on radiating energy until there's no more left. So this orbit will keep on decreasing in radius and eventually the electron is bound to fall inside the nucleus. So this tells us that atom is unstable and it cannot exist. If electron falls into the nucleus, then atom will no more exist. But this is not what we observe because all the material objects, even our human body itself, it is made up of atoms at the tiny scale if we see. And these are not collapsing instantaneously or at some time. So this was a drawback of Rutherford's model, which he could not explain. So then came the Bohr. In order to overcome, let me just write Bohr's model of an atom. Before that, in order to overcome the objections raised against Rutherford's model of an atom, Rutherford's model of the atom, or you can say to overcome the drawbacks of the Rutherford's model of an atom, Niels Bohr's, Sir Niels Bohr, put forward his own model of an atom, of the atom, which is now known as Bohr's model of atom. So it should be clear that to overcome the drawback of the Rutherford's model of the atom, Sir Niels Bohr gave his own model. And what does this model say? It has 2 points. It said that Only certain special orbits known as discrete orbits of electrons are allowed inside the atom. Let us have a look at an image also to make it clear what it says. Suppose this is the central portion, that is the black dot. Now I have made it blue. That it is the nucleus of the atom. What the first point says is that only certain special orbits. Orbits basically means the closed path which electron travels, like this circular path is closing in itself. Starting from here, it comes back and it ends again here. So electrons can only take certain special orbits, and these orbits are called discrete orbits of electrons. What does it mean by discrete orbits? Suppose this is first orbit, then the second orbit, it cannot be just anywhere like of any radius. There has to be a certain radius of which the second orbit has to be. So this means discrete, that these orbits can only take up some special radius, or you can say discrete radius, not continuous range. It cannot be of this radius because there is no orbit you can see here. So only discrete values of radius for the orbit. The second point which Niels Bohr made was that while revolving in discrete orbits, the electrons do not radiate energy. What it means is that, as we know that the accelerating charged particle, or you can say a particle which is moving with uniform speed in a circular motion, is accelerating again. So it will radiate energy in form of electromagnetic waves. But Bohr's second point said was that while revolving in these discrete orbits, the electrons do not radiate energy. That is, when the electron is, say, moving in this orbit, it will not radiate any electromagnetic radiation. Its energy will remain constant. So this will lead to that the energy being constant, the radius of orbit will not change. Pardon my drawing, but this is not changing. It's only it will keep like this. Excuse me. The orbit's radius will keep on being constant. So eventually the electron will stay like this and it will not fall onto the nucleus as was happening in Rutherford's model. Just one sec. So this was the second point, but he did not mention why the electrons do not radiate energy. He just mentioned that electrons do not radiate energy. It was a postulate, something that he postulated, but he did not like couldn't figure. He did not explain how. So, and it's not explainable by the classical picture itself. We use the semi-classical picture, which uses a bit of the quantum mechanics also to explain why the electrons orbiting around the nucleus do not radiate energy and their orbits remain of fixed radius. So moving on, that these orbits in which electrons are present, these orbits, what is orbit? Orbit is basically circular path, or we can say closed circular path. in this case. So these orbits, or these are also known as shells. These are called energy levels. As you can see here, these orbits are also known as shells, and these correspond to some energy levels. The first orbit, it is it corresponds to n is equal to 1 energy level. This n is the energy index, and they are also represented by a corresponding alphabet. Like n is equal to 1 shell, it, it is depicted by the alphabet k, that is k shell. N is equal to 2 is the L shell, and is equal to 3 is M shell, and so on. So what does energy index mean is that for a particular electron revolving in this orbit will have a fixed value of energy. And similarly, if electron is orbiting in the second shell, then it will have a different energy but a fixed value. Let me quickly write is that electrons revolving in particular orbit have particular, or you can say fixed value of energy. That is what it meant. That is what it is meant by energy index. You can say like electron in first orbit has energy E1, for second orbit it's E2, and so on for the nth orbit. You can say it's En. Okay. One second. Yes. So basically, at the end is that the orbits are the shells and they represent energy levels which electron can possess. And we saw that these orbits are discrete, that is, radius is discrete. So energy is also discrete. Just excuse me for 1 second. Hello. Yeah, I'm back. There was some noise. Sorry for that. So continuing, as I said that the orbits are discrete implies that the basically radius of orbit is discrete. So at the end, eventually the energy will also be discrete because electrons will have only particular energy in a particular orbit. So far, electron and proton were discovered. Electron is negatively charged particle and proton is positively charged. Electron has a very small mass as compared to the proton, and proton is the heavier particle among the two. I cannot change the pen. Okay. In 1932, James Chadwick discovered another subatomic particle. In 1932, Sir James Chadwick discovered another subatomic particle which had no charge, and its mass was nearly equal to that of the proton. So there were two features about this new subatomic particle: that first, it had no charge, it was a neutral particle, and second, that its mass was nearly equal to that of a proton. And it was eventually named as neutron. The third, the third subatomic particle, and it is denoted by an. It is denoted by an alphabet N or letter N. These neutrons neutrons are present inside the nucleus of all the atoms, except there is one exception, except hydrogen atom. The nucleus of hydrogen atom does not contain any neutron. There is only one proton in the nucleus, and in the outer first orbit there is one electron. This is the H atom. There is no neutron in it. Otherwise, say for example, helium, hydrogen helium, it has two proton and two neutron inside the nucleus, or the nucleus is made up of two protons and two neutrons, and there are two electrons in the first orbit. So the center of the atom, that is as defined by Rutherford, the nucleus, the neutrons are present inside it along with the protons. And the total mass of an atom is equal to masses of all the protons plus masses of all the neutrons and plus, one second, masses of all the electrons. Since the mass of electron is very small as compared to the mass of neutron and proton, the mass of an electron is of the order of 10 to the power minus 30. Actual mass is 10 to the power minus 31 into 9.1. And mass of a proton and neutron, you can say approximately it is 10 to the power minus 27. So it's approximately, the ratio is 1800. Mass of proton and mass of electron. So this third term, it can be neglected when these two other masses are being added. So we can simply write it as, by neglecting, what I mean is that suppose uh, you have a number 1000, and to it if you add a small number, say you are adding zero, not decimal value, suppose you are adding 1 to it, so it will become 1001. But we can approximate this 1001 as 1000 only, because there is not much change. So if this number is more bigger, say 10,000, then it is more easy to approximate it as 10,000. But if it is a small number, say 1 plus 1, we cannot approximate it as 1. It will be 2, as it is a double quantity. We cannot write it as 1. But for large values, the if the number is small which is being added to it, we can neglect that number and say that the result is still what we had earlier. So now the mass of atom will here become mass of protons plus mass of neutrons. Mass of atom is equal to mass of all the protons plus mass of all the neutrons. So now we have three subatomic particles. So let's write in order. First is electron, negatively charged particle. Second is proton, a positively charged subatomic particle. And the third one is neutron, which has no charge. It is a neutral particle. This was discovered by Sir J.J. Thomson. This was discovered by Sir Ernst Rutherford. And this was discovered by Sir James Chadwick. So now we have finally three subatomic particles inside an atom: electron, proton, and neutron. Let's quickly do an example to see how the sum of masses of protons and neutrons gives us the total mass. We have an example. Let me write the question quickly. It is an NCRT question which is inside the text, the small questions. Helium atom has an atomic mass of 4u and 2 protons in its nucleus. How many neutrons does it have? Sorry, does it have? So let's solve this question. We are given that helium atom. We are given with the helium atom, and it is given that the mass of the whole atom is 4u. U means unified mass, or you can simply say units. And 2 protons in its nucleus. There are 2 protons in its nucleus. It is asking how many neutrons, number of neutrons, how many neutrons are present inside the helium atom, or you can say nucleus. because neutrons are inside the nucleus only. So it is simple how to do it. You can use this formula, this one. Let quickly. Oh, let's use this formula which we discussed a few moments back. Mass of total atom, it is given to us. It is 4u, and number of protons are given. So the mass of proton, we can write it as number of protons into mass of one proton, and mass of neutron can be written as number of neutrons into mass of one neutron. Suppose we have 10 neutrons, so and mass of one neutron, it is equal to 1 unit approximately, and this one also 1 unit. Suppose we have 10 neutrons, that is n is equal to 10, and mass of one neutron is 1 unit. So total mass will be 10 into 1, that is 10 units. Similarly, here we are given with two protons and mass is 1u plus number of neutron into mass of one neutron, that is 1u. So this becomes 4 minus 2u is equal to nn into 1u. Here u and u will cancel the units. So this becomes nn is equal to 2. This is our answer. That is, there are two neutrons. So a helium nucleus is comprised of two protons. I'll draw it with another color. And two neutrons. This is a helium nucleus, and outside there are two electrons also. So this will be helium atom. Number of protons plus number of neutrons is equal to total mass. U just defines the unit of mass. If we simply add the number of protons and neutrons, we get a number, and if we put U in front of it, then this becomes the mass of the atom. Okay, let's move on now. So now the next question that arises, that how are electrons distributed in different orbitals, or you can say shells. These one we are talking about, these shells. How the electrons are distributed in this? How many number of electrons can enter into it? How for different elements like hydrogen, helium, lithium, beryllium, all these elements, how the electrons will be distributed. So let us now discuss that. So this distribution of electrons into different orbits, this distribution was suggested by Bohr and Bury simultaneously. They defined some rules which govern the distribution of electrons into these, you can say, the orbitals. Obviously, the first rule is that first rule of Bohr and Bury rules is that maximum number of electrons present in a shell is given by the formula 2n square. But what does it mean is that suppose we had shells K, L, M, N shell, and the energy index corresponding to them was 1, 2, 3. So in K shell, the number of electrons will be 2n square. And for K, n is equal to 1, so 2 into 1 square, that is 2 into 1 is equal to 2. Similarly, for L shell, the n is 2, so 2 into 2 square, that is 2 into 4. It becomes 8 electrons. Similarly, for M shell, 2 into n is 3 square, 2 into 9 is equal to 18 electrons, and so on. You can easily calculate it with it. What did the second rule say? Second rule was that maximum number of electrons that can be accommodated in a given shell is 8. Just bear with me for the time being. These are the rules as are mentioned in NCRT. So these are important to study, and I'll explain these other two rules, the rule 2 and 3, in few moments. And the third rule says that electrons are not accommodated in a given shell unless the inner shells are filled. That is, the shells are filled in a stepwise manner. First, they fill the K shell, then the L, then M. First, 2 electrons will go into K, then the 8 electrons will go into L. These numbers, which I calculated here, 2, 8, 18. If suppose there is only one electron in K shell, then the other electrons, say helium, it will not go into the L shell because this is not completely filled. The other electron also has to go here, then it will become 2. Then for lithium, the third electron will go into the L shell, like this. So rule number 1 is quite clear. That is, to calculate the number of electrons, we have the formula 2n square, where n is the energy index of the shell. Second rule is that electrons in the outermost shell are to be 8. Third is electrons are not accommodated in a given shell unless the inner shells to it are filled. There are some additional rules, or you can say these rules are not pretty well explained in the NCRT. So let me quickly write. This rule 2, you can say the electrons may go into the new outer shell, although the inner shells are incompletely filled. May go into the next shell, although inner shells are not completely filled. But there are certain specific instructions or rules which govern this also. It cannot just take any arbitrary configuration or any random configuration. Rule 3 is that the outermost shell cannot have more than 8 electrons, and the next inner, that is the penultimate shell, cannot have more than 18 electrons. What does it mean is, let me explain quickly. Suppose this small dot is nucleus, then this is K shell, then this is L, M, is it? K L M. First two electrons will go into the K shell, then eight electrons will go into this L shell, then M shell will start filling. So M shell can have 18 electrons, right? But suppose if there are 8 electrons in this, and now for new element, the next element, one more electron has to come. But the Bohr-Bury rule says that the outermost shell cannot have more than 8 electrons. So what will happen is that, sorry for the drawing, the next electron will go into the N shell and they will remain 8 here. But this is also another rule that even if the capacity of the inner shell exceeds 8, it cannot have more than 8 electrons unless there are 2 electrons in the outermost shell. What does it mean is that, as I just said, that this, if this is the outermost shell, the M shell, its capacity is 18 electrons, but we cannot put 18 electrons right into it because it will violate the second rule, that is, outermost electron should have 8 electrons only. So instead of filling this M shell with ninth electron, that is more than 8, we have to start filling the next shell, that is N. And here you can see that the inner shell M is not completely filled yet, but we have started to fill the nth. And this is somewhat not explained in this third rule in the NCERT, that is, electrons are not accommodated in a given shell unless there is the inner shells are filled. So what will now happen is these electrons will not start going into the M shell until there are two electrons in the outer shell. So there are 2, 8, 10, then there are 8 again, 18. For potassium, that is 19th, and for calcium, that is 20. After this, the 21st element, that is scandium, the electrons can start moving into this M shell again and will keep on moving into it until it becomes 18, which is the maximum occupancy for M shell. So these are the rules. You can say continuation in that rule 4, that although the outermost shell, that is say M shell, can have more than 8 electrons, but it will violate the second rule, that the electrons cannot exceed than 8 in outermost shell, right? So instead of going into the M shell, the electron will start going into the next shell, that is the N shell. For M, N is equal to KLM 1, 2, 3, and for N is equal to, for capital N, N is equal to 4. So now the electron will start going into N shell until it becomes two electrons in the N shell. Then, if there are at least two electrons in the outermost shell, then the other electrons for the next elements, they can start going into this M shell. Then we can have electrons greater than 8 because now the outermost shell is N, not M. We have drawn here also. When M was the outermost shell, only 8 electrons could go into it. But now N is the outermost shell and there are 2 electrons in it. That is, electrons are less than 8 in outermost shell. So we can freely now put electrons into it up to the limit 18. So it will follow the Bohr-Bury rule also, and we can fill the electrons as the new elements come. To make it more clear, let's see some examples, some nice schematic representation, so it will make more clear how this Bohr-Bury rule is used to fill the electronic configuration. This is the structure of oxygen. Oxygen atom O. It has atomic number 8 and mass number 16. That is, there are 8 protons and 16 minus 8, that is also 8 neutrons and 8 electrons. Electrons, protons, neutrons, 8, 8, 8. So now we will apply Bohr's Bury rule to fill the electrons into these orbitals. Sorry, orbits, not orbitals, shells. So for this first shell, that is K shell, there are 2 into n square. N is 1 for K. So 2 electrons. So we put 2 electrons into the first shell, and out of the 8 electrons, 2 electrons go into the K shell. Now we are left with 6 electrons. So what is the next shell? Next shell is L shell. The capacity will be 2 into n square. N is 2, 2 into 2 square. So it becomes 2 into 4, that is 8 electrons. And we have 6 electrons to still to fill in the oxygen. So the electrons will go like this: 1, 2, 3, 4, 5, 6. So 8 electrons will be accommodated in this way: 2 in the innermost, that is K shell, and 6 in the outer L shell. It follows the Bohr-Bury rule also. That is, the outermost electron cannot have more than 8 electrons. So 6 is less than 8. This configuration will work. Let's see other examples also. More examples, the better it is. Let us see for chlorine now. Chlorine is 17Cl35. You will have to work out the number of electrons, protons, and neutrons by maths. I'll just write them straightforwardly. So electrons are 17, protons are also 17, which is this number, and neutrons will be difference of these two numbers. That is 35 minus 17, which is equal to 18. So now we have 17 electrons to be filled in the shells for case of chlorine. So how will we proceed? Again, K is equal to, for K shell, N is equal to 1. So number of electrons in K will be 2 into 1 square. That is 2 1 square, the first rule of Bohr and Bury rules. It will be 2. 2 electrons go into this first K shell, this one. This one is the nucleus, the yellow portion. Then for L shell, N is equal to 2. So the capacity is 2 into 2 square, it is 2 into 4, 8 electrons. So once we subtracted 2 electrons from 17, the 2 electrons, these 2 electrons, they go into K shell, we are left with 15 electrons. Out of these 15 electrons, 8 will now go into the L shell. Okay. So 8 electrons are now in the L shell. So 15 minus 8, we are left with 7. 8 goes into L, we are left with 7 electrons. Now the good thing here is that the capacity of L is 8 itself. So it will not be any issue if we apply those simple rules that outermost cannot have 8 electrons. But as the number of shell increases, it becomes uh, little bit clever to fill the electrons, but it's still easy. Those other few rules start coming into act, the penultimate rules, the rules regarding the penultimate shell, which I will discuss those also in few moments. So now 7 electrons will go into the M shell where the capacity is 18. So they will directly go into here. This was L, this is M. 1, 2, 3, 4, 5, 6, and 7. This is the configuration of chlorine. Third point. Take it as an exercise. You have to calculate the number of electrons, protons, neutrons, and other things, how they'll go into the shells by proper maths. I'll write it quickly, directly now. I'll post the assignment also later for these questions. For argon, we have 18 electrons, 18 protons, which we are interested in. You will calculate the number of neutrons and all. Homework. Okay. So how will 18 electrons go? K shell has occupancy of 2, L has 8, M has 18, N has 2 into 4 square, it is 32, and so on. So 2 electrons go into K. So 18 minus 2, 16. Out of 16, 8 go into the L shell, 2 go into K, 8 go into L. We are left with 16 minus 10, that is 6 electrons. So this is argon, right? So out of 18, 2 go into K. So we are left with 16. 8 goes into the L. We are left with then 8. The last 8 will go into the argon. Up to here it is very simple. Up to the first 18 elements. Things bit little bit more clever from this next example. That is the next element, which will be potassium. It is number 4. Yes. For potassium, one second. Yes. For potassium, we have 19 electrons. This is nucleus. 2 go into K. 8 will and 8 will go into N. This is up to argon. But now one more electron is there in potassium. So the N shell still has vacancy of 10 electrons because the capacity of 10 shell is 18 electrons at max. But the Bohr-Bury rule number 2 says that number of electrons in the outermost shell cannot exceed 8. So if I put the ninth electron in the N shell itself, so number of electrons will become 9 in the. This will violate the, or it will break the second rule. So instead of going into the N shell, now the outer shell, that is M shell, the next shell, will start filling. So the electron will go into the M shell. So the configuration will be 2, 8, 8, 1, 2 in K, 8 in L, 8 in M, and 1 in N. Although the M shell is not completely filled because M has occupancy of 18, so 10 vacancies are still there, but still the N shell has started to fill. These are the two rules which I mentioned separately. This one, two sub rules you can say under the rule fourth. And we will also see that these electrons will keep on going into the L until there are two electrons. Just let's see the example quickly. We'll understand it better. After potassium comes calcium. Now for calcium also, it has 20 electrons. this element also, first it will go up to 288, that is argon, same configuration as argon, 288. Then the 19th electron, that is for potassium, will come. So it will not go into M, because if we put the electron here, the outermost shell will have 9. So 9 is greater than 8, but it should not be greater than 8. So what will happen is this one electron will go into the N shell. So the configuration is 2881. All right. So outermost electrons in outermost shell will be now less than 8. So it will follow Bohr's-Bury rule. Now for calcium, one more electron comes. Next shell is not 2, it is still 1. And this was the second part of the fourth rule, which is here. Until there are 2 electrons in the N shell or the next shell, the electrons will greater than, first it will become 2 only, right? So it becomes 2, then they will start filling into the N shell. So to make it 2, this other electron for calcium also will go into the N shell. So it becomes 2, 8, 8, 2. Total is 20, that is calcium. So you can see here also L, 8 in M. Interesting in the sixth example, that is the next element for after the calcium. Just bear with me. Yeah, it's still recording. I'll quickly reopen it maybe. Now the next element is scandium. It has 21 electrons. Now what will happen? Up to argon 288. 2 in, let me write it on this side. 2 in K, 8 in L, and 8 in M. Now the 19th will not go into M because it will become greater than 8. So that cannot happen. So the electron goes into N. For 20, that is calcium, the electron will still not go into M because the number of electrons in N is not 2. So it will again go here, it becomes 2. Now there is the 21st electron in scandium. Where will it go? In M or in N? The answer is it will go in the M shell. Why? Because the fourth part of the rule 4 said that if the number of electrons in the outermost shell becomes 2, then the electrons can start going into the inner shell if it has occupancy more than 8. And since M has occupancy of 18, this electron will go into this shell, the M shell. So it will become 9. So this will be the configuration. That is 2892, which is written here, shown here in the, that is 2 electrons in K, 8 in L, and you see there are 2 electrons in N, and 8 were there, and now the ninth electron also is in the M shell. This is the essence of Bohr's-Bury rule. If you still have any doubts, you can post it on that Aksharamaala platform, or you can join the class next time. So you can ask there, I can tell you nicely. Seventh, let's see two more examples. Now we know the rules completely. This is for cobalt. Cobalt has 27 electrons. K, L, M, N. 2 electrons go into K. What am I writing? 8 electrons go into L, 8 go into M, 2 go into the K, L. In L, there are 8 electrons. In M, there are 8 electrons. This becomes now argon. 19th electron go into N. 20th electron go into N, which becomes 2. Now it's 20. 21st electron and the following electrons can start going to M shell because there are 2 electrons now. So it is now 20 and more electrons are 7 electrons are left. So it has occupancy of 18 and 18 minus 8 is 10. So yeah, 10 electrons can be easily filled into it. Sorry, 7 electrons because it can hold 10. So now 7 electrons will go into this. It will become 15. So this will be the 288, sorry, 28152 for scandium. 28152. 2 in 2 in K shell, 8 in M shell, sorry, L shell. 2 in K shell, 8 in L shell, and these are, if you count, 15 in M shell. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 2 in the outermost shell. Outermost shell, there are 2 electrons, that is less than 8, so it clears the, or it follows the Bohr-Bury rule also. And in the M shell, there are still 3 occupancies left. And it is still not complete, but we have started filling N shell also. It is the second part of fourth rule. Hope things are clear. Let's see another one, last example quickly for today. For copper, L, M, N. 2 will go into K up to helium, then neon, then argon, then up to potassium, sorry, calcium, it will go into N, not in M. Now from calcium, it will start entering into M. So it has 10 occupancies left, and copper has 29. All right. Up to here, how many are filled? Up to here, 2, 8, 8, 20 are filled. So 9 are still left. 9 can go into easily into that. So it starts filling scandium 21, titanium 22, vanadium 23, chromium 24, scandium, vanadium, chromium, manganese 25, ferrous, that is iron 26, uh, cobalt 27, nickel 28, then 29th will be copper, and 30, that is zinc, can also come into it, but we have 29 electrons for now. So this time what we see is that there is a slight difference instead of the 9 electrons directly going into it. So what is the difference here? Uh, if we follow the rules, we will end up using that 9 electrons go into it, and 9 plus 8 is 17, right? And we still have one more electron, so this configuration should be fine. That is 2, 8, 17, and 2, which sums to 29, right? 2, 8, 10, 17, 27, and 2, 29. But the copper's configuration is little bit different. You see that instead of 9 electrons, this 1 electron from here also goes into the M shell. So instead of 17, now we have completely filled, that is 18 electrons in the M shell. So configuration is like 280, 2, 8, 18, and 1. This is actually an exception. And you'll learn about it in future that the last electron, it goes into, if I'm not wrong, into the 4s orbital. It occurs so because it is more stable this way. The one electron from the 4s, it will jump back to 3d9 and it will make it 3d10. So the d subshell will be completely filled and only one electron will be left with the 4s. So this is an exception to Bohr's-Bury rule, you can say, for the stability of the atom. So let's quickly summarize what we studied. We saw the why Niels Bohr gave his model, because to overcome drawback of Rutherford model, overcome drawback of Rutherford. Then we saw the Bohr's model itself. Electrons orbit around nucleus, but in discrete orbits, and he named them as shells, which were represented by K shell, L shell, M shell, and energy index also 1, 2, 3, and so on. Electrons would revolve in that and will not radiate energy, but did not tell why they won't radiate energy. The answer lies in semi classical physics, which uses the ideas of quantum mechanics, which is not required in 10th class. So, moving on. What we did next was the discovery of, not discovery, but the third subatomic particle, that is neutron, which was discovered by Sir James Chadwick. Yes. Third particle, that is neutron. Then we did an example for the mass of atom, how are electrons distributed, the Bohr's-Bury rule, and all those examples. Neutron, the third subatomic particle. And after that, Bohr and Bury rule. And we did then some examples for it, for various elemental configuration. So that was all for this class. And just ask doubts if you have again in the next class. We'll post it on the Aksharamaala platform, as always, I say. And thanks if you are watching this video. Signing out. Date today is December 22nd, 2021, 7:17 p.m. Stop the recording. Yes. I'll share the recording with you later.